Ma'am, are you sharing the slides? Because your slides are still not visible. And you are also muted.
Hello, I'm trying to share the screen. Why doesn't it allow me to share? I just saw. Yeah, share. Just let me.
Yes, we can now see
Please
your slide.
share full screen, and we can hear a lot of noise. So your voice is coming very faintly.
Hello, ma'am. Hello, ma'am. You are not audible. Ma'am, you are muted.
Ma'am, you are muted.
Can't hear you.
Am I audible now?
Yes, but with
Yes,
the
clear.
noise, can you speak
Am I
again?
audible now? Hello,
Yes,
am
you
I
are.
audible?
Joey, you are audible. This is Usha.
Audible? Yes, hi Usha.
Hi,
Yes,
hi.
can everybody hear me nicely?
Yes, we can all hear you.
Okay,
So,
now just let me know if you can see the screen.
yes.
Okay.
Okay.
Is it full
Just
screen? Full screen?
full screen. Yes.
Okay.
Okay. Okay. So I will be chairing this afternoon session. Again, welcome to you all. I am Usha Devi.
Mm-hmm.
So, okay. Thank you. So we have 5 talks today in the afternoon, in between a tea break and a poster session. But right now, Joey from IIT Delhi, Professor Joey Ghosh from IIT Delhi, who is in a quantum photonics group, who is interested in nonlinear optics and waveguides and quantum processes. And her talk is an entanglement distribution of 100-kilometer range polarization entangled photons. So over to you, Joey.
Yes, thank you, Usha. I just switched on the video once more. Can you all see me as well? Hello, Usha. Am I audible? And can you all see me as well?
Yes, yes.
Okay, great. So, hello everyone. Welcome to this afternoon session. So, after lunch, I presume I can preserve your attention. Uh, so thanks first of all to TCG Trust. Thanks to Dr. Pankaj Agarwal for personally inviting. for this. Calcutta is close to my heart because it's my hometown, and I would have loved to come and join in person. But given the professional commitments here, it was a little difficult to join in these days. Okay, so today in this session, actually, I'll be speaking about all fiber integrated tunable polarization entanglement distribution. Uh,
Hello.
Polarization,
Hello,
yes,
can you hear me?
yes,
There's a lot
Isha.
of disturbance. Lot of disturbance. Is there any? Can you improve your audio from that side?
Um, I'm trying to see. Just
Oh,
one
it's
second, huh?
okay otherwise, but we are not able to get you very clear.
Yeah, I see that.
Lot
I
of
see that.
disturbance.
I see that. I'm trying to actually speak loudly as possible. Uh,
If
I'm
you, ma'am,
hoping.
if you please be a louder, then I think it would be okay. Yeah.
Yeah, I'm trying to speak as loudly as possible. Yeah. Um, okay, let me just start. I mean, if it's a problem, so today this is the best I can do. Uh, yeah. Is there still noise?
It's okay. A
It's
bit of
okay?
noise, but it's okay. It's okay. Yeah.
Okay, 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 great. So I'll be speaking about this all fiber integrated entanglement distribution experiment that we did at Telecom Wavelengths. And this was a distribution of about 100 kilometers that we were able to achieve through fiber entangled photons. And this has tremendous applications. As we all know, this is the era, the quantum era, and particularly for long distance, fiber optical quantum communication network, this has a direct connection. And it is particularly interesting for multi-user PKD over metro area fiber optic network. So as we all know, without spending a lot of time, because this is an audience where I suppose people are from the same background and from the same community. But I just thought I'll flip anyway a few slides in the introduction. So we know that in today's sensitive data that is encrypted and sent across fiber optic cables, as we know it, the digitized information, and so in across these channels, they are sent as digital keys that are needed to encode and decode the information, right? And we popularly follow the RSA method, public key encryption, that relies on the factorization of very large prime numbers, right? Now, both in this classical cryptography, both data as well as keys are sent as classical bits, as we know. So, in the form of a stream of electrical pulses or optical pulses, representing 1 and 0. So this makes them very vulnerable, as you know, because smart hackers can read and copy these bits of information while they are in transit. Now, so this definitely poses a threat. And today, in the era of quantum computer, this is an additional cybersecurity threat because for the quantum computer, breaking this encryption methodology, which relies again on the factorization of large prime numbers, is a mere tool for the quantum computers, right? So, quantum security is actually the need of the hour. Now, what do you mean by quantum security? As we all know, quantum security refers to the use of quantum mechanics to secure and transfer data. Right? So, and quantum mechanics provides a powerful tool. For example, its features such as the no cloning theorem, the measurement problem that leads to state collapse, and also the fact that measurements are irreversible in quantum mechanics. So, all these things actually provide the quantum security, which is the background security. So typically, photons of light are used for transmitting data along optical cables, and they can also take on a state of superposition, which is allowed in quantum mechanics, which means that they can represent multiple combinations of 1 and 0, and just not 1 or 0, but multiple combinations of that as well. So these are typically qubits. So utilizing photons, you can have photonic qubits, right? And the beauty of these qubits is, from a cybersecurity perspective, we know that if a hacker tries to observe them in transit, their super fragile quantum state collapses to either 1 or 0. which means that the hacker cannot tamper with the qubits without leaving a telltale sign of this activity. So with all those features, the realm of quantum communication and also utilizing quantum key distribution is a tremendous powerful tool in today's cryptography, quantum cryptography. So what is QKD or quantum key distribution? It involves sending encrypted data as classical bits over networks, while the keys to decrypt the information are encoded and transmitted in the form of qubits. Right? So here QKD is different, or the quantum communication part is different from the classical cryptography. You can still transfer the data in terms of classical bits, but the key to decrypt them or encrypt them is in the form of these qubits. Now there are different QKD protocols. We'll be discussing in the next slide. Now, one thing to note here is that the implementation of QKD needs to be carefully considered, as in QKD, the endpoints are the weakest part of the system. Now, there are some security considerations in QKD. So, as we know, we can broadly classify QKD under two classifications. One is the prepare and measure based protocols, which are single photon based protocols, and the other is the entanglement based protocols. Now, the prepare and measure based protocols, there are many types. They're very popular. For example, the BB84, the B92, the BPS QKD protocol, the coil state protocol, etc. Right? Many of these QKD protocols are actually achieved through attenuated laser pulses, and the use and the simplicity of doing it is one thing, but it is also prone to different kinds of attacks, such as the photon number splitting attack, the intercept decent attack, etc. On the other hand, the other broad classification of QKD is under the umbrella of entanglement-based protocols. Now, entanglement-based protocols, of course, uses quantum entanglement in the heart of the QKD protocol. There are two different kinds, the ECR91 and the BDM92 protocol, which are in use. And why this is more special or more secure, this actually is the gold standard for security in quantum communication. Why? Because these protocols are based on true single and entangled photon sources. They rely on Bell's inequality test, which is the CHH's Bell's inequality test, which certifies that it's a true quantum source. The inherent randomness in the source gives the high security that is required in the communication. Then, on top of all of this, no cloning definitely makes the system resilient to eavesdropping attack. Entanglement by itself as a property offers long transmission paths, and because entanglement relies on these non-local correlations, there is an inherent source independent security. So there is the absence of what is known as trusted nodes. So all these features actually make entanglement-based QKD very secure, and it ensures that the entangled photon pairs used for key generation and distribution remain shared between the legitimate parties only. So now the motivation for entanglement-based quantum communication network, I have been talking about it, all of this, but now there's a lot of activity and a lot of current research for long-distance QKD and quantum communication network. So here is a QKD network, which is consisting of this kind of multi-user star network. So the need of these long quantum communication, or huge multi-scale quantum communication network is that the scalability and security of any of these quantum communication networks depends on widespread connectivity, which means that your system should be multi-user and just not between one Alice and one Bob, but multiple Alices and multiple Bobs. So it should be multi-user. Secondly, the system should be trusted node free, as we just pointed out. In entanglement based QKD, there is an absence of trusted nodes. So that is one of the feature. Then there is compactness. The system should be compact and easy to deploy. So this means that a full fiber integrated, portable kind of system would be the need of the hour. And of course, the system should be highly efficient, which means that there is high brightness high brightness of the even the qubits or the the QKD rates that we are talking about. So the entire quantum source should be highly bright. Number of photon pairs per second should be very high. So all of this tells you or insinuates that there is a requirement for an efficient, multi-user, fully fiber integrated entangled photon pair source. And polarization entanglement is very popular and easy to generate as well as manipulate. So polarization entangled photon pair source. So with all these kind of features. So these are some signatures. So like concurrence, fidelity, Bell's inequality. These are. I just thought I'll just flip this slide because we know about all of this, and these are routinely the parameters which I um, used to qualify the quality of entanglement in some sense. Now, the generation of heralded single and entangled photons, they rely heavily on this nonlinear optical technique of spontaneous parametric sound conversion, that whereby you pump the nonlinear crystal with pump laser, and this due to this interaction, there are two photons which are correlated. These are known as signal and Eigner photons, and they definitely preserve or they obey energy conservation as well as momentum conservation. Now, relying on SPDC, you can have different kinds of photon sources. So you have both free space as well as fiber-based sources. But for this particular talk, our group actually experiments on both these systems, both free space as well as fiber-based sources, quantum sources of entanglement for quantum communication. But in this talk, we will be mainly focusing on the fiber-based systems. A little bit, one slide to talk about our group a little bit. And so this is the quantum photonics group in IIT Delhi in the Department of Physics. And we have several interests. We work on fiber-based quantum communication as well as free space. And then there are other interests like coherent light-matter interaction. We also work with silicon on insulator nano waveguides, then squeeze light generation. So these silicon nano waveguides are, again relying on another nonlinear optical technique, which is four-wave mixing. And through these techniques, again, you can generate entangled photons or heralded single photons. Right. So this is in a nutshell what our group does. So there are lots of activities that are going on. These are just snippets from our lab. And this is our group. We heavily collaborate with Professor Vivek Nektar from the Electrical Engineering Department. There are several PhD students as well as masters and BTech students, and we also have some postdocs. Now coming to the main two regimes. So quantum communication happens under the optical band, which is typically in this wavelength regime, and also in the telecom band, utilizing fiber integrated sources, fiber-based sources, and so we will be mainly focusing on the fiber-based source. So in our group, actually, we have fiber-based quantum sources, there are different kinds of prototypes, and we work on both type 0 as well as type 2 quasi-phase matching. So here is a source that is a broadband telecom photon source, all fully fiber integrated based on type 0. The spectral brightness of the source is about 2.5 to 10 to the power of 7 when we characterize this from this publication. And there is a maximum coincidence to accidental ratio of about 700, which is a characteristic of this source. Now, another source, fiber-based, fully fiber-integrated source, relies on type 2 phase matching. Here, there is a different kind of entanglement that can be generated compared to this one, which is a broadband source. And the type 2 phase matching, of course, is less efficient than the type 0 one. So here, our spectral brightness is of about 10 to the power of 6 pairs per second per milliwatt per nanometer, and the maximum power is pretty high. So for this particular talk, again, now I'm going to focus on this broadband source that we can channelize into multiple channels and thereby have multi-user kind of a scenario. So under this, so this is a high brightness telecom photon pair source. First, we will be talking about the broadband polarization entanglement, and then we will be going on to this multi-user QKD. And also, what we have been able to achieve in this particular experiment is to do 2 phase matching. Here, there is a maximum coincidence to accidental ratio of about 700, which is a characteristic of this source. And also, what we have been able to achieve in this particular experiment is to do 2 phase matching. Here, there is a maximum coincidence to accidental ratio of about 700, which is a characteristic of this source. And also, what we have been able to achieve in this particular experiment is to do a tunable polarization entanglement. So there are two different types of polarization entangled states, and the source is tunable from one to the other. So this is a very significant feature of our source because it makes it more flexible. In addition to being highly efficient, multi-user, fully fiber integrated, compact, portable, all those things. But I mean, it's also a tunable entangled source. So first coming to the fully fiber integrated high brightness source of broadband polarization. So there are certain things I'm going to discuss here, and this is a good piece of work which has resulted in optics and laser technology, and it has also resulted in an Indian patent that we have filed last year. So now coming to, so this is how our telecom photon entangled source looks like. So here actually, so this is in SINAC interferometer. We use a tunable laser at 775 nanometer, and using a WDM, we pump a type 0 PPLN waveguide from both sides. Using a WDM and a fiber PBS, we pump it from both sides, and therefore it is in SINAC interferometer. And the photons, which are signal and Eigner, are also generated from both ends. Now there is a 90-degree fiber twist that we use on one side to change the polarization of these outcoming photons, and therefore ultimately the photons that come get combined through the fiber PBS and get channelized through the WDM because they are at 1550. They are in this HH and this VV combination. After a long pass filter, of course, you can eradicate the pump photons, and what you are remaining with are the signal and Eigner photons, but they are uh, in this polarization ambiguity of this HH and VV as they come out from both sides of the waveguide. So, so when we characterize our source, these are some of our parameters. We estimate the brightness. So this is a source. The initial paper was featured a brightness of about 10 to the power of 7, and this one is in SINAC geometry, and therefore the brightness has enhanced, and we've been able to improve our parameters to 10 to the power of 8 pairs, 2 into 10 to the power of 8 pairs per second per milliwatt per nanometer. So this is one of the brightest source not only in India but also even internationally, and we compete very well with some of the international Type 0 based fiber integrated sources. So our maximum coincidences to accidental ratio, which is also a parameter for the G20 cross correlation, is about 1000, and this is how typically CAR varies as a function of the pump power, and the green graph is the CAR, and these are the blue ones are the accidental counts, whereas the orange ones are our measurements from the coincidences. Now this is typically broadband source, so there is the coincidences of the photons are emitted in this entire bandwidth, which has a full width at half maximum of about 52 nanometers, and these dots are actually coincidence measurements from our source. So it spans the entire band from 1520 to about 1580 nanometers. Now, how do we entangle them? So we use broadband polarization entanglement. So this is the entangled state, and this is how we characterize it. So this is all these parameters on, and this particular two photon interference regime. This is for a pump power of only 1 microwatt. So with 1 microwatt pump power, we have very high brightness. We are not, so we should not be also using very high pump powers because we want to have good entanglement quality. And with high pump powers, of course, we can crank up the pump power to have more photon count, but those are, we have to be worried or we have to be careful about multi-photon emission events. Okay, so we keep the pump powers very low, and we only pump with about 1 microwatt of power. And so this is the entangled state, and this is typically our raw visibility in the mutually unbiased basis of H, V, D, and A. And this is also, there is a violation of the Bell inequality, and the visibility is also pretty good. It's definitely always more than 92%. And yes, from our experimental data, the CHS Bell inequality is about 2.49, and this violates by 29 standard deviations. So more, maybe I will skip a few slides. So this is about the quantum state tomography that we do to, experimentally measured fidelity is about 90% and the concurrence is about 83%. So these are the raw parameters, and of course the background corrected parameters are much. The fidelity is about 94%, whereas the concurrence is close to 90%. Now coming to the multi-user source, so banking on this broadband telecom source, we are actually interested to show the multi-user feature of this source, and we've been able to do pretty well. So this has resulted in an Indian patent that was granted earlier this year, and this is now published in APL Quantum, and yeah. So this is the 100-kilometer multi-user source that we are talking about. So banking on that same source, I will be skipping some of these parameters. It's just that here maybe I just point out that in order to do this multi-user feature, we use an array waveguide grating, and for that characterization was required so that there is no crosstalk between the neighboring channels. So this particular graph here shows you the channel number for the array waveguide grating, because this has many channels and they are separated by about 100 gigahertz. There are 32 channels, and in the ITU grid, and the channel spacing is about 100 gigahertz. And these are the typical, wavelengths. So this is the characterization here, and this shows that these yellow boxes are actually our coincidence detections. So we do a coincidence detection across this entire graph, but this shows that it's only there is a one-to-one connection between the channels that are correlated, showing the beautiful, so there is no channel crosstalk, and yeah, all of that. It was important to verify that. So this was a detailed characterization that we did. So now coming to this multi-user polarization entangled source. So what we did is, so this part of the source is the same. We utilize a CL band splitter, and then you have your tomographic, polarization analyzers in order to do quantum state tomography. Then after we do that, we again we combine it with a CL band combiner, and this is just to facilitate easy characterization of the AWG and the way we characterize the entanglement. But for long distance transmission, of course, we should be directly plugging them into the AWG without using the CL band combiner. So coming to more details, so this tells you that there is entanglement over 14 pairs, and this has been also characterized. So this is just we take a particular pair, a particular channel pair, which is C38 and C31. So C38 is somewhere here, whereas C39 is somewhere, C31 is somewhere here, and they are symmetrically located left and right around 50-50, which is our line of degeneracy for this particular source. Now we characterize that.
Hello.
Yeah, just two
we
more
have
minutes.
only 3 minutes.
3 more minutes, and I will wrap up. Yeah, Usha, thank you. I'll wrap up. Yeah. So this is one channel pair that we have characterized. So for 14 such channel pairs we have characterized, and we have shown that the source is tunable between two different kinds of polarization entanglement. One is the phi plus belt state, and the other is the phi minus belt state. And these are our quantum state tomography measurements. That shows this particular characterization. This is one particular channel pair, and we have been able to do the entanglement characterization. It was important to characterize them across all 14 channel pairs. And this is our characterization of fidelity. Each of these dots, for example, the red one here and the red one here, these are the C38 and the C31. Similarly, you have C44 and C25 and so on. So the fidelities are always higher, and this is the regime that shows that it is always in the quantum regime, and the classical regime is this shaded portion. And yeah, then this is also characterization of our concurrence, and this is also characterization of the S parameter. So we have seen this for all these 14 channel pairs individually, and although this has been seen for the 14 channel pairs, and we've been able to see this tunable belt state between 5 plus and 5 minus across this 14 channel pairs. But the source can actually, we only measured in 14 channel pairs, but the source is much more broadband, and it can go up to 40 channel pairs. So in that sense, it is many more multi-users actually. The multi-user is to up to about 40 channel pairs. Now, so this is, I will just skip this slide, and just coming to this last slide. So, in order to show long distance entanglement distribution, which we've been able to achieve about 100 kilometers using fiber spools, what we did is, after the long pass filter from the SINAC interferometer, we directly plugged. After the long pass filter, we are only remaining with the entangled photons that we plug directly into the AWG. And from the AWG, there are several channels. So in order to characterize each channel again, so let's say for example, this channel 38, this is plugged onto this big fiber spool, and channel 31, which is its partner channel, has been plugged onto another big fiber spool. Now, after doing this long distance transmission through these fiber spools, then again we do the polarization analysis for the quantum state tomography, and we characterize our entangled state using this mechanism. And this is at the end of 100 kilometers, as you can see. So this is a 5 minus bed state. And this is a table to show that when you have 50 kilometers on Alice and 50 kilometers on Bob, so this is just one channel pair, right? So these are some of our numbers. Our coincidence, the raw coincidence rate is about 25 per second. And if we have, this is only done with quantum efficiency of about 20%, using single photon detectors which are portable but spans at telecom, and they are not so efficient. But if you use SNSPD detectors which have very high efficiency, you can actually extrapolate this number, and it is actually about 500 per second. Now, when there are no fiber, like let's say the Alice is only 1 meter fiber, whereas Bob has about 50 kilometers, these numbers can go up to about 2.7 kbps of rates, right? So this is something that now fidelity is also constantly high, the concurrence is high, and the QBER that we have been able to generate is about as low as 5%, and it is below 11% for sure, because we do BBM 92, and this is so less than about 9% in that. So this is, we also did polarization mode, characterization, just to show that because we are using long fibers and we use single mode fibers. So this is starting to do that. And currently we are also trying to do a field demonstration in the IIT Delhi campus using this particular source. So thank you for your patience. Yeah.
Thanks,
Questions?
Joy,
Yeah.
for the interesting talk. It's open for discussions. One or two questions.
Ma'am, you told that if we increase the power, ma'am, you told that if we increase the power too much, there is a probability of multi-photon emission. Suppose if we take a DNAT case and we pump the crystal with a 405 nanometer, you're supposed to get 810. So does it mean that we'll get multiple number of 810 instead of 2, or something else?
So any of these processes, they have to actually obey conservation of energy, right? So there are also higher order, nonlinear optical processes that are possible, right? So these,
Okay.
so of course, so the 810, of course, will be generated for the second order nonlinearity.
Okay, so I didn't get that.
But it could be the multi-photon generation could be close to that, right? So instead of 2 photons, you can also have other photons, right? So 4 photons or 6 photons, when you crank up the power. So of course you can actually possibly also have 810, but there are also probability of higher order effects, right? And all of these, any of these photons, they will actually create a noise background for your detection, right? Which is not good for your entanglement quality. In any case, for the true entanglement, right, for the actual entangled photons, you have to then, filter out, any of these events. So then why generate in the first place, right? So the entanglement quality actually becomes bad. Your visibility of the two photon interference experiments and all of that become bad. So we have also seen it for high powers, and we clearly see that the fidelity and the quantum state tomography. So fidelity is of course one characterization of that. All of that actually go down when we try to do this as a function of the pump power, and we try to crank up the pump power. Of course, the coincidences and all that we have, they go up. So there are also photons generated around that wavelength then in some sense.
Ma'am, if we use a bandpass filter, is it possible to avoid?
I don't think so. Yeah, I don't think so. I mean, like very narrow bandpass filters. This is a broadband source anyway, right? For us, we have to retain the broadband characteristic of this particular source because we are interested in channelizing them, right? So the broadband feature is important. So if you use a too tight, because within that broadband, which is about 50 nanometers, right, you can also have several other spurious photons, which is not, So simply, it is difficult to probably difficult to discriminate which are coming from multiphotons, which are coming from the true single entangled photons and all. So the best mechanism is to do a characterization with respect to pump power, and we see the highest the pump power where we obtain the highest fidelity, right? And of course with a reasonable rate, we usually keep that. But for communication, as you know, we also need a good rate, right? A good rate of photon pairs for the key rate, basically, right? So there is a balance between a good key rate as well as the entanglement quality. So we do an intelligent, balance out optimization of those two things, and then these results. Right?
Okay.
Yeah.
But I just have a curiosity question. First of
Yes.
all, let me congratulate you on these recent achievements and
Thank you,
wonderful
Isha.
patents. I just wanted to ask you if pair sampling loophole, if it is taken in a long distance entanglement distribution, how
Yes.
would you fare in your long distance
So this long
polarization?
distance, so these long distance simulations, these long distance results, we will not be getting these entanglement results. As you can see, the quantums and the fidelity is not that high, right? So it is also after 100 kilometers, right?
Yeah.
So we are losing many photons, right? These are typical, dark fibers, like optic fibers, right, at telecom, and they have about a loss of about zero point 0.2 dB per kilometer, right? So and so for typically 50 kilometers long fiber spool has a propagation loss of about 13.5 dB at 1550, right? So we are losing many photons also in the process, right? And this is a single channel. So out of those 14 channel pairs, or the source is actually much broader, broadband, right? We are only looking at a very narrow band there, and we are trying to channelize that in 14 channel pairs. Now,
Okay.
out of that, we are just looking. So this experiment is only one channel pair.
Okay.
So in one channel pair, there are only a few photons, and you're propagating them for 100 kilometers. So there is a huge loss, right? So definitely, in these experiments, we have not retained our pump power to 1 microwatt. The pump
Okay.
power has gone up. It has
Okay.
gone up to a few milliwatts, and which also, which is also the reason, but because the source is otherwise highly efficient. Just at the in the lab and without before 100-kilometer propagation, there might be many photons, yeah. But because we have this propagation problem of very long distance, right, where somewhere we are trying to compromise the entanglement quality with the key rate. So this long distance experiment wouldn't have been possible if we didn't use a slightly higher power. So as you can see, the entanglement quality has decreased a little bit. Definitely it has decreased. So these are, we are only catching pairs and we are trying to do this. So because we bank our thing on coincidence detection and we are doing all these experiments based on the fact that they are pairs or coincidences, right? But nevertheless, still then, the quality has decreased.
Okay.
Okay, but because there must be multi-photon events, and so at the end, in order to have a good key rate and all of that, we are also, balancing out on this. But if you see our in-lab experiments, which are before, So these are in-lab experiments. This is a characterization of one channel pair within the lab, and just with
Okay.
1 meter fibers, right? So
Okay.
here the fidelity and concurrence is much high. So the entanglement quality is much high.
Okay.
And so I will not be able to comment much on the pair sampling
Yeah.
simulation, Usha, but I mean, I think one can do that for long distance thing, whether you're actually using pairs or whatsoever, right?
All
So, but
right.
our experiments show that, I mean, without the pairs and without the entangled pairs, of course, we will not be having those results, particularly also our Qbert. This is a fidelity, sorry, coming to that, yeah.
Fine.
Yeah.
Okay. Thank you very much. Let's thank the speaker for once again.
Thank you. Thank you.
So now next
I will just,
talk is by our young and energetic friend Dr. Manik Banik. So he doesn't need an introduction in this crowd, but still let me do the ritual. Manik is associate professor in St. Joseph's Theoretical Science, and he is known for his work on quantum foundations, quantum communication, causality in quantum theory, and other interesting aspects. So, with this short introduction to a very famous person here, so let me give it to him.
Yeah. Touch this object and I know the shape, whether it is circular or triangular. But since I am in a dark room, I cannot know the color of the object. And let's say I am interested to know the color of the object. How we can know it? I can make a pinhole in this box and look through it, and I know the color. And since I don't know see the full object, I don't know the shape. But let's ask this question: is there a possibility that I can know both shape and color? Yes, we just open the box. We know shape and color. Similar, lots of example I can give. Let's say I want to know my height. At the same time, I want to my temperature. Everything I can know simultaneously. But quantum world is peculiar. In quantum world, there are complementarity principle holds, and that is actually first pointed out by Niels Bohr in this 1927 conference, Como, Italy. And this paper was written in 1928, this famous paper, Nature paper, and you will get a very good history of how this complementarity he is introducing in this studies of histories in philosophy of science. This very good paper, I find one of them. So what is complementarity? So in quantum world, there are some property we cannot know simultaneously. What is this example? Okay, in double slit experiment, path information and interference visibility is the complementarity behavior. Similarly, position and momentum of a particle is complementary property. Similarly, spin of a particle in different direction are complementary property. So now, then when quantum information come up, measurement we used to know according to von Neumann that okay, sum of projector adding up to identity. But once the quantum information information theories, they come up with that okay, mathematically more rigorously we can formulate it. This von Neumann measurement we can actually generalize to more general POVM kind of things, positive operator valued measurement. And once this POVM is introduced, we can actually make measurement which are not jointly measurable now jointly measurable, of course with some inherent degree of fuzziness or imprecision. And let's look into the simple example, the spin half system. So as we know, for spin half system, most general state is described by a density operator with M being a vector with norm less than equal to identity in R3. And if we look into this projective measurement will be this one with A is plus minus taking value plus 1 and minus. Jointly measurable if there exists a POVM. Yeah. So if there exists a joint POVM, you see it is characterized by all this sequence of number taking value 0, plus 1 and minus 1. But POVM means all they should be positive operator and add up to identity. Not only that, if we sum up over all the index apart from J, that should give me the jth unsharp observable. If it holds for all J, then we say such a joint measurement exists. Now that is very popular result by Paul Bush again, that if we take spin observable along x and z y direction, you can take any two orthogonal direction, they will become jointly measurable if and only if lambda is equal to 1 by root 2. Sorry, not if and only if, up to 1 upon lambda, 1 by root 2. Of course, if I can do jointly measurable up to 1 upon root 2, any value less than 1 upon root 2, you can jointly measure. But now you see, if we take three observable, x, y, and z, again, all are mutually orthogonal space direction, the joint measurability condition, the unsharpness parameter further get down 1 upon root 3. And that is the optimal we can do. That is very famous result. Okay, but why to study incompatibility? Because recently people have found that this incompatibility is deeply connected with other foundational concepts like Bell non-locality and Einstein-Podolsky-Rosen steering. I am not giving the individual citation, I am giving this review. Here the proper, all the citation, most of the citation you will get there. Not only that, there are lots of information theoretic protocol. I think tomorrow Archanda will talk more on that. There also incompatibility play again a role. That is also again I put here a review of modern physics. So this indicates that this recognition has motivated a deeper explanation of incompatibility from a foundational perspective. What we can say further. including scenario involving multiple copies of quantum system per experimental run. So this is the, so far we have, I don't know, we have found only one work in that direction. This Carmelli et al. In 2016, they have introduced this concept. It is published in Mathematics, but I'll recommend this paper should be more visibility, should get more visibility. That is a very beautiful idea they have introduced. Let's try to understand the idea. Okay, as I said, X and Z measurement we cannot jointly know. Let's say in per experimental run, I give you 2 copies of the state, same state. Can we know X and Z? The answer is obvious. On first copy, I perform X measurement, and second copy, I perform Z measurement. So given 2 copies per experimental run, we can perfectly know 2 observable. But the situation becomes more interesting if I per experimental run give 2 copies of the state, but I ask you to tell me the value of X, Y, and Z. Now what we can do? Now one main strategy is that on first copy, I perfectly know X. And the second copy, I do the Paul Bush mechanism. Because Paul Bush say how to make it unsharp and how to do joint measurement for Y and Z. And up to what lambda we can do? According to Paul Bush theorem, lambda is equal to 1 upon root 2. But what Carmelli et al. They have identified, this mechanism, what I have just said earlier slide, that is not the best one. Because it is in a sense biased towards X direction. X become perfect, but other two become more imperfect. You treat them all symmetrically. Then there is a way out to make this better. That means you take these 2 particles, do a joint measurement on these 2 systems. You obtain some statistics, and from these statistics you just post-process and try to get the statistics of Z lambda, Y lambda, and X lambda. And you see, now you have a lot of power, new power here is coming. Because since these are 2 copies, now here you can consider in principle entangled POVM. And they have shown that, okay, their result I will tell. Now how they define, what is their definition? Again, I am telling in spin-up system, that given M measurement and K copy of the system per experimental run, how to define joint measurability. The set of spin observable Sn is said to K copy jointly measurable if there exists a POVM G tilde, which is positive operator on the K tensor product Hilbert space. All are positive and add up to identity on K tensor Hilbert space, and then reproduce the marginal condition. And here marginal condition, you have to be careful. This operator acts on Kth tensor product of the rho m, and if we sum over all index apart from J, it should give me the statistics of this POVM, unsharp POVM on rho m. And what they have shown that for XYZ observable, the unsharp parameter value now becomes root 3 by 2. There is an improvement. In earlier case, it was 1 upon root 2. This is a bigger value. So you can do more sharp measurement if you follow this strategy. And this is the observable I am written here, which do this, achieve this value. And here this double curly bracket is the double commutator, but not in commutator true sense. U comma V double commutator is U tensor V plus V tensor U. And what they have also proved, this is the best you can do. This is the optimal. Given 2 copy, you can do, this is the best things you can do. Yeah. Lambda is equal to 1 upon root 2. Average, that is not make a good sense. Like I am saying I am looking into worst case kind of things, look into RAC scenario. I am looking to the worst case things, what is the success? Then it is clear advantage. Of course, average here it is not a meaningful quantity. Look into the worst case scenario. This is advantage. So that is I think this is a new kind of idea they have introduced. Carmelli and Heinosari and other their collaborators are there. But unfortunately, I don't know, it is 2016 work, but still not got that much visibility. It should get more. So what question we asked? Okay, we ask the question, if instead of parallel, why I am saying parallel? Because okay, m direction, 2 copy of rho is given. I am saying instead of that, let's say I prepare the state m direction and I give this anti-parallel direction, minus m direction. Can we do something better? This is the question precisely we are asking. We investigate whether such enhancement persists or can be improved when instead of two identical parallel spin states, each experimental run involves one spin and its flip counterpart. Okay, what is the motivation of this question? Okay, partially the motivation comes from this work by Nicola Gisa and Sandu Popescu, where they have shown that spin flips is anti-parallel in some communication tasks can contain more information than parallel. So we ask this question, but in joint measurability. And what is our result? This is the theorem. Your lambda will become 1. So you want to know 3 Pauli, X, Y, and Z. I give 2 copy, you can perfectly know. This is all. So there is no unsharpness. All these things are perfect. The statistics. And what is the proof? One line proof, because I give you the operator that reproduce its positive operator, add up all these things. If you add up all ijk take plus minus values. If you add up all ijk, all these terms will cancel, and 8 terms are there, so it is identity 2. And all are positive operator. How to check that? 4 cross 4 matrix, I take the eigenvalues, all are positive. And if I do the jk sum, it reproduces the statistics of x. If I do the ij sum, it reproduces the statistics on z and the other things also. That's done. Okay. Now, this operator has something more interesting feature, what we observe. All of them are rank 1 operators, but proportional to rank 1 state. And if you try to suitably draw the orthogonality graph of this 8 state, you can represent in a vertex of a cube, and the orthogonality is each of the vertices is orthogonal to their diagonal, means to the other vertex which is phase diagonally connected. Means if you take psi 1, it is orthogonal to psi 2, psi 4 and psi 7, because these are phase diagonal. Similarly, here I have shown another example, psi 6, it is phase diagonally connected with psi 3, psi 5 and psi 0. So this is just an observation, nothing more so far we have extracted from here. But we ask the question, okay, I give this example and it's showing it's already 1, but what is happening? Why this anti-parallel is giving me more power? Is there a better way to understand that? To address this question, I like to take a detour. Here the concept of our mathematical framework of GPT helps us. So what is GPT? GPT is actually formally introduced in 1960s. Ludwig, Milling, McCoy and lots of other people for the axiomatic derivation of quantum mechanics, and recently it regained new interest from the quantum information perspective. So in a GPT, a system is specified by its state, effect and transformation. And what is a state? It's a convex set, and generally we are looking into finite dimensional convex compact set embedded in some real vector space. Effects is, and sometimes we will try to represent the unnormalized state, so it forms a cone. What is the effect? Effect is the dual cone of this state cone. Let's try to look into one example. For quantum mechanics, the state cone is nothing but set of all positive operator, unnormalized. If we want to normalize state, we have to take the trace 1 condition. And its dual cone is nothing but same, identical. That's the beauty of quantum mechanics, it's self-dual. And some of these effects add up to identity, forms a measurement. So now that is not all. GPT also has to have some other responsibility. It has to also specify how to describe the composite system. So in the morning we have listened one talk by Giulio. Here he has considered composition, but he has not, in his composition, local tomography is not satisfied. So that means what is the question? I have a single system, SA and SB. It is completely specified by their states cone, effect cone, and transformation, and so on. So what is the composition description? So here we have to little bit careful. So what we demand? First demand is it should give me consistent. What is meant by consistent? A valid state on this composite system on valid effect should give me positive probability. Otherwise, I cannot give the meaning to that. Second is we also want our theory to satisfy no signaling condition. That means no instantaneous or superluminal communication is possible. And third condition is local tomography. What does that mean? That any joint system, by doing local measurement and then these two distance parties talking to each other classically, can reconstruct the state, know the state. That condition we are taking. So if we take these three natural, apparently natural condition, I don't know, to me these two are very natural, but in quantum foundation community people take this also, then this Namioka and Fels, they have something interesting result. Still your composition structure is not unique. There are infinite possibilities, but this infinite possibilities lives between these two extremal, maximal tensor product and minimal tensor product. In maximal tensor product, in minimal tensor product, it is very obvious, easy to understand. Here only separable or product kind of states are there. And what is effect? Any mathematical object which gives me consistently. That are all allowed effect. Here we take another assumption that is called no restriction hypothesis. If a effect or state is mathematically consistent, I will a priori not discard the state from my theory. That is called no restriction hypothesis. A priori will not put any restriction. And maximal tensor product is opposite. So for our purpose, let us try to see the definition of minimal tensor product for 2 qubit. So each of the system is locally quantum and qubit, but according to these things, I can define lots of composition. What is the minimal composition? So in minimal composition, we have only separable state. And what is my effect? Anything that gives me consistent probability according to these three, no signaling, consistent probability, and local tomography, that is my valid effect. So now it can be shown, there are some relevant work, that in minimal tensor product, your state space is only separable, whereas your effect now gets enlarged. Quantum mechanics, your state space is red, and your effect space is also red. It is a self-dual. But in minimal tensor product, you reduce your state space, but your effect space get enlarged. So now we have an intuition how to understand that. This enhancement of joint measurability in anti-parallel ensemble. This gives a understanding. Let's try to see. So that is another way to put the theorem. The observable now ask the same question that okay, x, y, z I want to know on anti-parallel ensemble, on parallel ensemble. No, let's don't go to anti-parallel question first. Let's go to parallel question, but ask the same question in minimal tensor product. That is our theorem. The observable x, y, z are 2 copy compatible, 2 copy parallel compatible for any value lambda in between 0 and 1 in minimal tensor product theory. So how to prove that? Again, by construction, I have to give a operator which satisfy some of them as identity and reproduce the marginal condition. But look carefully, this is not a positive operator. But that is not my demand also in this theory. My demand is this operator should give me positive probability on product state. That's all. Because in this GPT theory, my only states are product state and their convex mixture. So positivity demand is only on product state. So this satisfies this. So in other words, how to understand that why this enhancement is coming in minimal theory? Because when we are asking this question in quantum mechanics, Carmelli et al., they were asking, okay, you prepare 2 state identical copies inseparable, but you try to search your POVM onto this red color state. And you can go up to root 3/2. But now in this toy theory, we are allowed to enlarge my search space because these are also valid POVM in this theory. And since it is enlarged it has a large space, there is a scope that we can beat their bound root 3 by 2. And that is precisely happening. And this is this operator. Now look at one interesting feature. This is the flip operator. What flip operator does? If you apply flip operator on this rho m, it perfectly gives me the orthogonal state, perpendicular direction. Or I should more precisely, I should write at rho minus m. On this flip operator, if you apply on this POVM on this minimal tensor theory, this is just a simple calculation. If you will get exactly the POVM what we have written in antiparallel case. Just a simple one-line calculation. Now look into this trace rule. So flip, composition flip is identity. So here I can write flip. So this hash rho m tensor rho m, here I can, instead of identity operator, I can write flip composition flip, because identity is flip composition flip. Now using this dual map concept, one of the flip I can bring here. Now flip operator has beautiful property, it is its dual, operator dual. So now this identity, this flip will come here, one of the flip, it makes hash to be this antiparallel operator, and one flip remain here, it makes this here. So what we are trying to say, if you try to pose the question in minimal theory, it gives a better mathematical picture, at least what is happening, why we are getting this enhancement. And actually this framework, introducing this GPT framework, actually gives the scope to ask a more generic question. That instead of 2 copy of rho or rho perpendicular, you give rho m and lambda rho m. Where lambda is any CPTP or PTP map. CPTP means completely positive trace preserving map or positive trace preserving map. Then will there always be is there an advantage over parallel? So here we prove an interesting theorem, very generic theorem, this one. You take arbitrary ensemble. It is, I am not talking about X, Y, Z measurement, arbitrary ensemble. So let's say lambda prime optimal ensures joint measurability of observable SN on this ensemble, on this configuration, rho m tensor lambda rho m. We are trying to tell this lambda prime value is always upper bounded by the value of lambda optimal, which we can obtain from parallel configuration. When this lambda is any CPTP map. For any CPTP map, this lambda prime is always upper bounded lambda optimal. So if you want to get this advantage, this map must be PTP, positive trace preserving. If it is CPTP, it will not give any advantage over parallel configuration. How much time ahead? Okay, fine. So now that raises naturally the question, okay, is this the case that all PTP map will be advantageous? Okay, that is we don't know simple answer. In general, it might be a hard question, of course. We have not explored yet, but we give one example. This is a class of one parameter family of map. For this lambda value 0 to 1, it is a PTP map, and for lambda is equal to 0 to 1/3, it is a CPTP map. But for mu beyond 1 by 3, does it always useful? At least for X, Y, Z measurement, what strategy we are taking, for that it is not helpful. F is flip operation, the flip operation, what I have defined. But this question is remain open because we are only searching for a XYZ ensemble of observable, and we are following only a particular strategy. So this question is open. So in general, the question is whether all PTP map will be useful for giving advantage over this parallel configuration. So in short, so that's what I said. So far we have obtained this value. So what is the take home message? So we demonstrate that the antiparallel configuration enables exact simultaneous prediction of 3 mutually orthogonal spin component, an advantage unattainable in the parallel case. As we showed, this enhanced measurement compatibility in antiparallel configuration is better appreciated within the framework of generalized probability theories. Furthermore, this approach extends the study of measurement incompatibility to more general configuration beyond the parallel and antiparallel case only, providing deeper insight into the boundary between physical and unphysical quantum state evolution. So presently, what we are trying to do, trying to analyze, okay, let's say I go to some of my experimental friends and I try to say, okay, let's try to perform an experiment to show whether antiparallel is at all what we are theoretically we are obtaining is actually giving me advantage. But first, that friend will ask, okay, how many ensemble, how many state I will check? There are uncountably many infinite states. If I want to check if I want to reproduce the statistics on uncountable many state, that experiment means my lab will be occupied for my whole year, means it will impossible physically. So that's why we are asking, okay, can we show this difference for a finite set of ensemble? And there are very intuitive some argument to say, okay, if this finite ensemble is from a great plane, then of course the gap will vanish. It has to be at least 3D figure. So this kind of question we are trying to explore. And lots of other question in principle can be done. We can take many measurement, not 3, let's say 10 measurement, and we can give 8 copy. And some of these are flipped version or maybe some joint PTP map. In that case, can we have more advantage? These are the question. In principle, one can try to further explore in this direction. So finally, I'll end my talk with a quote by one of my favorite scientists, Manamin. What he said. What happened? Okay, let me read it. Relation between authors and referees are of course almost always strained. Authors are convinced that the malicious stupidity of the referee is alone preventing them from laying their discoveries before an admiring world. Referees are convinced that authors are too arrogant and obtuse to recognize blatant fallacies in their own reasoning, even when these have been called to their attention with crystalline lucidity. All physicists knows this because all physicists are both authors and referee, but it does no good. The ability of one person to hold both views is an example of what Bohr called complementarity. Thank you. Yeah. Take your parallels configuration and then rotate it to anti-parallel. But yeah. Does it tell me that the value of lambda will continuously? Yeah, but yes. Correlations among your talk, of course, you did not take any subject. Yeah, it's correlation, no?
No, measurements are
correlated. Yeah. So let's see your first question. That flip I cannot give because there is no universal flipper. That's why I say if you know plane, the gap between parallel and anti-parallel will vanish. That we know from remote state preparation, all these things. A universal flipper doesn't exist. But here you look how we are posing the question. To the device, I am preparing the state and I am giving at per experimental run. So that's why it will not that much come. And the second question, that's why I say the GPT gives them better mathematical picture what is happening. But why physically what is happening? Maybe angular momentum conservation, something, but something we are still missing. What is the physics reason for that? That is not very clear also to me. Mathematically we can see, okay, because now I have a search space is larger because I am searching over POPT state. That is not clear. Yes. Yeah. But that's why I say universal flipper doesn't exist. That is a one-line argument, linearity of quantum mechanics. That's unitary antilinear. That will be not linear. Linear, it will say that there is no universal flipper. Then I can do remote state preparation with one CBit. That I can do only great plane, great circle. If you know the state, you do, as a measurement device doesn't know the state. I am providing the state to the measurement device is blind to the state. No.
I can look for a necessary and sufficient condition, then there is something.
So that
which is lambda, which is
yeah, that is a question. But I'm saying you cannot make it perfect. That is obvious.
Proof of principle kind of.
Nice talk. So, so I was wondering whether one should go beyond quantum theory like GP to figure out what is the reason behind it.
Again, I think mathematical.
So what about going to the the dilation field where you take the UVM and dilate it to projective measure and see what is happening, because there you can have some symmetries.
Yes, that might happen, but that's why I'm saying Carmeli paper, they gives a very beautiful condition. But if and only if condition no, that they derive root 3 by 2 up to XYZ. They say, okay, you follow this mechanism, any arbitrary direction you can give a if and only, but that becomes computationally hard.
No, I mean that is, but even for spin spin measurement, even if you don't take orthogonal,
yes,
still you have some bound on the unsharpness.
But 2-copy level now the question becomes difficult.
It becomes difficult, but in principle one can figure out.
Yes. So I'm saying that's why I'm saying if you give me take arbitrary set of things, give me the best bound for parallel, I can try to compare with anti-parallel in principle, because I can write a SDP for that.
Of course. Now, in the case of the state estimation, the argument that why anti-parallel states provide you better estimations fidelity for state parallel is because it spans higher dimensional degrees.
Yes.
Okay. So maybe one can try to figure out similar things.
Yes, there is a quite possibility, because as I said, we go to minimal GPT framework to understand it better from a mathematical perspective. Physically, what is happening? Why it completely become perfectly jointly measurable because 3 direction I can completely know from parallel and anti-parallel. So what is something physics is going on?
Maybe
what is that? And that is not this what Nicholas Gisa and Popescu identified. That is not the reason. Something more deeper thing is happening here. That is also not very clear to us yet.
We can discuss during tea break. So I being the chair, I can't ask you questions now because I have to move on. Let's thank them. I have a lot of questions. So the next talk is by senior friend, Professor Devashish Sarkar, who is in Kolkata University, Applied Mathematics Department. He will talk about some recent results and status.
আমার গলা এমনি জোরে কোন চিন্তা হ্যাঁ আমাদের টিচারদের মাইক লাগে না ও ইয়া নো প্রবলেম So thank you, Usha, and also Pankaj. Where is Pankaj? So thanks to the organizer for giving me the opportunity to tell a talk here. Now, my junior colleague Manik just give a very big quantum mechanics things, and possibly in the ISI conference we are talking about the that last slide about about the are pure persons. Okay, permeates. Now my talk is regarding quantum state discrimination task, some recent results. Firstly, to motivate students, basically, I will give some results from older things, and in that works my friend Shivashish also there, and Gurda, and so all other people is there. But recently, my students Subrotu, Indranil, Otunu, they have done some work. I will discuss later on their topic. Now, here the basic task is to distinguish a class of states in a composite quantum systems by LOCC. The states are given orthogonal to each other, obviously, globally orthogonal they are. Therefore, all are distinguishable globally. The number of states given in what we choose are finite. Now, firstly, we will review some cases with pure bipartite states, single case, copy, and with certainty. The class of Bell states firstly, then generalized Bell states, and some other kind of things, in mixed kind of things, classical class of activable bound entangled states. Lastly, we will produce some results, recent results regarding distinguishable and indistinguishable aspect. Many new things generates last 5 or 10 years, and Manik is one of the Manik and their collaborators are one of the groups where they have found many good results in that field. Now, before going to the basic things, I just memorize the basic what do we mean by physical operation. Manik also shows that completely positive maps, and they could be written in this form, Krauss form, and this is the conditions on the Krauss operators. And a particular more useful in quantum information theory is the separable of superoperator. What are the form of the separable operator? All the Krauss operators can be decomposed in that manner. They are all linear operators, and that kind of operators are called separable superoperators. Sometimes separable superoperators are useful then, but there is a gap between LOCC and separable superoperator that is shown firstly by that Eric Chitambor and their group in 2010. Now, by LOCC, we mean a physical operation that each party can perform quantum operations in their subsystems and communicate their results, and this is to and fro. Okay, and that can be many rounds and okay. Now, our main things, discrimination tasks. The subject starts with one of the most striking invention by Bennett group, where you can find Bennett is always there in a big invention. Always quantum non-locality without entanglement. That is a paper, very big paper, where they have shown that a complete orthogonal basis of 3 cross 3, that is a product basis, however not distinguishable locally. Okay, complete basis. They also showed in that before in that year there is another one work, that is a concept called unextendable product basis. That means that product basis cannot be extended to the whole dimension, covers the whole dimension of that Hilbert space. That is in 3 cross 3, it is 9. And they have given only 5, and all the complementary subspace contains the entangled state. Okay. Now, quite contrary to that thing, those product bases are not locally distinguishable. Okay. Quite contrary to that fact, that we can think that entanglement will more vulnerable, but Hardy-Walgett in 2000 they show that any two orthogonal pure set, whether bipartite or multipartite, are locally distinguishable with certainty. They're quite contrary to this work. They have shown that any two pure entangled state that can be written in the form, and you can, by observation, you can show that these are locally distinguishable. They are using a linear algebra result, that simultaneous diagonalizability of the matrices. Using that result, they have proved these things. Consider now four Bell states. This phi plus minus and psi plus minus, they are not locally distinguishable. That is done by Guruprasad Sivasic, is one of the author on that paper. They are not locally distinguishable with certainty in the single copy case. And the proof is very interesting. Why? Because they have taken a very interesting symmetric kind of states given by Smolin. This is R4 plus the pairwise Bell states they have taken. These are projectors on Bell states. And where phi plus minus are the Bell states written in their possible basic, Smolin state these unlockable or activable bound entangled states. These are a kind of bound entangled states. If they are separated, they are bound. The states is symmetric with respect to all four parties, separable in 2 cross 2 cut. And if any two parties came together in a lab, then it is possible to share a Bell state between other two parties. Okay. Now, if Bell states are locally distinguishable, then by LOCC, only not coming together in a lab, any two parties can distinguish which Bell state they are sharing, and correspondingly, other two parties will share a definite Bell state. As the states is separable in any 2 cross 2 cut, this is not possible. So the proof is very intuitive by considering these small states only. In that same paper, Sivasic and Guruprasad, they have shown that it is also proved in that using a bound or distributive level entanglement, that even any three of the Bell states are not locally distinct. So the results are in opposite directions. Hardy's group proved that any two are distinguishable. Now, if we go 2 to 3, that are not locally distinguishable, and all the four are not. The problem of local distinguishability or indistinguishability in 2 cross 3 system is completely solved by Hardy-Walgett, in the sense that which 3 orthogonal pure state would be locally distinguishable, or which 4 states, that they have done in that work. Later, Hodeki group, they gave a condition for a complete orthogonal basis in bipartite system to be locally distinguishable or not. They have generalized the old result. If at least one of the states is entangled, then the basis is not locally distinguishable, and the basis is probabilistically distinguishable if and only if all are polar. Now, some interesting observations. Waterloo, in that 2005, constructed a class of bipartite subspace having no basis distinguishable by LOCC. Somsubro and Walgett, they have shown that any 3 linearly independent pure quantum states are locally unambiguously distinguishable. Runio, Duan, and they provided a lower bound on the number of locally unambiguous distinguishable numbers in any arbitrary basis. Walgett and Scott later showed a condition for unambiguous locally distinguishable random quantum pure states. Now, consider the case of generalized Bell states. So these are SUD group generated basis. Consider a full set of orthogonal maximally entangled states in D cross D. You can write down them in that form. All are connected locally unitarily by this kind of unitary operations. The class of maximally entangled states are known as generalized VLBCs. Now, one may ask about the maximum number of states that are locally distinguishable with certainty in single copy case. By using a bound on distributed entanglement, it is shown by Ghosh et al. In that paper, I am also an author, that no D+1 states taken from D square states are locally distinguishable. Shown that if D is prime, then any k states are locally distinguishable if k into k minus 1 by 2 is less than equal to 2. Clearly, any three from the set of D square sets are locally distinguishable. Later, Nathanson generalized this result of any three maximally orthogonal states in C3 using the existence of mutually unbiased bases. He found that the condition for a set of k maximally entangled states, result of Hahn is also established, and also established the results of D+1 states. All the above results do not provide us the condition that exactly D or less than D number of states of D square generalized Bell states are locally distinguished. These questions are unanswered. To proceed further, we go back to the teleportation protocol. Consider an arbitrary qubit phi. Use any state from the whole set of generalized Bell state. Teleport the above a qubit using the maximally entangled set as channel using standard Bennett protocol. As the protocol is fixed, therefore the qubits obtained after teleportation are different. Now consider any D or less than D number of generalized Bell state. If all the states found after teleportation are orthogonal or for at least one qubit phi, then the states are surely locally distinguishable. So it is sufficient condition for the local distinction. It is interesting to note that the condition for existence of such phi for D or less than D states is equivalent to the finding a solution of discriminating corresponding unitary operators of the qubits. Two observations: if two copies of each generalized Bell states are supplied, then by teleportation protocol, it is easy to show that the full D square set is locally distinguishable. If a set of D or less than D states are locally distinguishable, then corresponding the teleported states as basis, we can rearrange the state in such a way that so that they could be distinguished by only one way LOCC. This is another observation. Examples where teleportation protocol fails, there is a 6x6 dimensions states. These states by our teleportation protocol, this fails. There are also 4x4, 5x5. There are many examples in that paper. And this teleportation means one way protocol. Later, Ghosh, Sivasis, and Somsubro, they have separately proved that condition that by which the problem of local discrimination of the class of D maximally entangled set by one way LOCC resolved. They have resolved that problem. Okay, later on. Now I go to the another case of that activable bound entangled state. It is 4 copies of qubits. Now it can be generalized to more than 2n plus 2. These 4 states, there are 4 different unlockable bound entangled states into 4 qubits system. These 4 are mixed states, but you can argue the in same way for the Bell states, you can show that these 4 mixed states are locally indistinguishable. Okay, that what for the Bell state, you just add some other 2 dimensions to Bell state, then you have another state, and you can go the same argument, and you will find that these 4 mixed states they are locally indistinguishable. Yeah. Yeah. You can generalize the whole set by this. This is one of the work done by me, Indrani and Somsubra. That is, and Bhavani is also there. So they have the same permutation symmetry. They have orthogonality property. They are locally indistinguishable. These work actually done by me and Indrani, and all other things are done by we4. Now I am going to some recent results. Going from the argument of non-locality of without entanglement. We have discussed mainly several results on distinguishing the class of pure and also some activable boundary entangled state. But recently, entanglement assisted discrimination protocol generates further interested on main class of state which initially are locally indistinguishable. Looking back to the results of non-locality without entanglement by Bennett et al. And set of UVB in 3x3. In multi-party system, this concept is still studied incompletely, except for some special case of completely orthogonal product basis and some unextendable product basis. We now provide the results in three tripartite system which exhibits non-locality without entanglement, but are distinguishable if we provide some assistance of entanglement. This in 6x6x6 dimension, there are 36 states. This is locally indistinguishable. You can ask that what about 6? Not 6. You can go 2D cross 2D cross 2D. Then you have take D equal odd, then 18 into D minus 1 orthogonal products. You can generate. They can be perfectly distinguishable by LOC. Now, in that things, if you take D is even, then you have also some states of the same property. You can go to the odd number of dimension. Then this class of product states has perfectly distinguishable. These are some other dimensions, 2 odd and 1 even. You can generate class of states with the same properties. Now you can go to the all even. You have some states that cannot be perfectly distinguished by LOC. There are some distinguished, there are not distinguished. One may observe that each class of product states constructive are not UV. They are not always UV, but they are product basis. That is separate question. That is now they are all are separate. Initially, we are taken that question. We will deal in the next work. All the sets are not perfectly distinguished by this. This is because of the fact that local distinguishing is necessary to eliminate states of a given state, which is not possible in its given scenario. The special about the state is that they are LOCC indistinguished containing minimum number of states with respect to the dimension. Below that, there is no number. Because of the symmetric structure of those states, it indicates that no one of the three parties cannot eliminate any state from those states. Now, if we take that first example of 36 states, you can now distinguish them if you assist by a Bell state. No, sorry, one copy of GHZ here. One copy of GHZ. C2, C2, C2. C2, C2, C2. Bell state is given by some other set of examples by Cohen, firstly. That paper generates this entanglement assisted discrimination. In this, this is also this that 18 d minus 1 which we provide, that is also distinguished by LOCC if we provide one copy of GHZ. Since only one copy of GHZ, you can. There is also some other number of product bases you can distinguish if we assist by GHZ state. Since all the states are symmetric, it is really not important which pair of parties holds the resource state. Also, the required entanglement resource to accomplish the task of distinguished non-local state does not depend on the dimension of the subsystems. All the LOCC indistinguished sets constructed the theorem 1 to 6 are minimal in country. Also, the above class of states are minimal sets which are distinguishable through GHZ. We observe advantage by using entanglement as a resource for discrimination of subsets. There are some open problems. The first is to find LOCC in distinguished sets of lesser number of states for arbitrary high dimensional multipartite system. This is an open problem. Second, the question of optimality of entangled resources used in discrimination problem. We have taken a GHZ class. You can think of less entangled state by which you can do. We cannot claim that this is the optimal thing. These questions are open. In a given Hilbert space, the subset constructed here are small sets. That is, the number of states contained in the set is much lesser than the net dimension of the Hilbert space. Hence, an essential search in this direction is to find out the number of orthogonal product states from which no one can eliminate it by orthogonality preserving positive operator value measurement. Explicit construction of such set also important for any multipartite quantum system. So there are many things open in this. There are some results from Manik's group also there. Now, the last part of our talk, another work, recent work, very recent, that is last year we have published almost. It is a direct consequence in quantum cryptography like data hiding, secret sharing. One question emerged that if there are only local sets in our hand, how can we transfer them into a resource that have applications in data hiding? So you have local sets. Can you have some hidden non-locality? This is so that non-locality can be activated, and later on you can give a protocol of data hiding or something else. This is actually Manik's group asks this question very early. Here comes some trivial sets, or non-trivial sets, not trivial, non-trivial sets with this property, and that initiated the perception of local redundancy. An orthogonal set is pronounced to be locally redundant if it remains orthogonal after discarding one or more subsystems. Apart from that, it is called locally irredundant. This is one by Somsubro and Saronath's work. This generates this question. Now, Bandyopadhyay Haldar first revealed that there exists some orthogonal sets free from local redundancy, and that can be distinguished locally, but under some orthogonality preserving measurement. Each outcome will lead to a locally indistinguishable. This phenomena is known as genuine activation of non-locality. The term genuine denotes that the sets must be free from local redundancy. Later, Li and Zheng, they extended the result by addressing two types of genuine hidden non-locality, type 1 and type 2, and came up to a locally distinguishable set of bipartite product states which can be deterministically converted to a locally irreducible set via OPLM. After that, Hossettle gave a scenario for the activation of strongest possible kind of. The genuine activation of non-locality for the multiplier series is not fully explored. Still many open questions which are not been fully known. Is there exist a local set in which local activation is not possible? But to activate non-locality, two or more parties can join together. That question is unanswered on that. In our work, we have tried to explore that solution using only LPCC, not full LOCC, local projective measurements with classical communications. And if it is done, then there is a gap between LPCC and LOCC, you can always found. That we have found. More precisely, we encounter two distinct types of local sets within n-party quantum system, say S1, S2. None of these sets can be directly employed to transmit hidden classical information because we know that the information encoded in locality is always fully locally. But a possibility arises when we consider the potentiality to activate non-locality within S1 through local operations. In the context of data hiding or secret sharing, it is possible to effectively turn such a resourceless state to a resourceful. We show that such a set can be converted to a locally indistinguishable orthogonal set by LOCC with certainty. This transformation allows us to locally hide information within S1. That is the information encoded in S1, which is locally available in S1 after transmission cannot be accessed completely by local observers. Part of the information always hidden. Okay, this is the motivation, and we form the pictorial things in C323 contains 9 mutually orthogonal product states locally distinguishable under LPCC. These are the 9 states. You can separate the blocks and you can find that things, which are the states. And they are locally independent, non-locality can be activated by LPCC. In S2, on the other hand, S2 represents such sets where genuine activation of LOCC is impossible. There are separate things happens in quantum theory. So the classical information encoded with orthogonal states of such set always remain accessible to the local. That is, when parties are constant to perform OPLM, the outcomes consistently exhibit locality. The characteristic places S2 on more local than S1. This is the characteristic of two different states. Now, how we can find that? There is also, we can found that kind of class. These are 9 states. They are locally redundant. Non-locality cannot be activated by LPCC. Bob Charlie jointly can activate non-locality by giving PAMs. Pictorial things. So local projective measurement, this is the last slide. Measurements and classical combination is a strict restriction of LOCC. Therefore, a consequence is that any task which is feasible in LPC, so they are in LOCC, but the converse is not. We find there is a gap between LOCC and LPC. Other results, asymmetric configuration also gives some non-locality without entanglement. Also, we have found some results where the round number is important. How much classical information is needed, it is also important. And there is also some extension to this class to we have multipartite systems. Then we can think of unextendable biseparable basis. And that work is also some other works we have done recently. That is also published. Okay, thank you.
Maybe one short question, because we have a tea break. Before that, we have one more. not to ask you to raise discussions during tea break. So let us thank the speaker once again. Thank you. With pleasure that I invite Dr. Arpita Maitra. So okay. So
University of Hyderabad.
Dr. Arpita Maitra has done her PhD from Computer Science Department, Jadavpur University, that I came to know, and she was working as assistant professor at C.R. Rao Advanced Institute of Mathematics, Statistics, and Computer Science before she joined here at TCG Crest at IEA, some branch here. I think it is in a different floor. So we have been able to kind of have a superposition TCG Crest floors. So it is with, she works on security analysis. So let me give it over to you.
Thank you. Yeah. Thank you, Professor. And thank you, Pankajda, for inviting me, for giving me this opportunity. So today I'm going to talk about quantum secure communication theory and practices. So this is general kind of talk. I want to highlight the gap between theory and practice. So that because quantum communication, we assume that this is secure. Theoretically, it is secure. There is no doubt. But what happens if we want to implement that without evaluation, just believing that this is quantum, we are getting security from quantum mechanics, so we are safe if we deploy this without verification. So what will happen? So in this talk I will discuss that. So quantum communication, what is quantum communication? In classical domain, communication means transfers of bits. Quantum domain, this is qubit. So transmission of qubits. I'm skipping this because you already know what is qubit, the superposition of, and what is the difference between bit and qubit. So I'm skipping these slides because time is very short. So this is the measurement, you all know that. And you also know that one may theoretically pack infinite amount of information in a qubit through that alpha and beta. Alpha and beta are complex numbers, and you can express those alpha and beta infinite number of bits. And in that way, you can pack infinite number of information, infinite number of bits into a qubit. This is a huge advantage in quantum mechanics, but it is not clear how you will extract that information. For that, to extract that information, you need infinite number of same qubits. So that is not very clear. In actual implementation of qubit circuit, it might not be possible to perfectly create a qubit for any alpha and beta. Technology is still at early stage. Lot of problems in computation, storage, and communications are there. Now you know that quantum communication means your communication. So from where this security is coming, one thing you can express qubit as a superposition of 0 and 1. And when you will measure that qubit, you will know that we will destroy the qubit. We will get either 0 or 1. So original qubit will be destroyed. So this is actually gives us security. How? So this the beauty of qubits from a cyber security perspective is that if a hacker tries to observe them in transit, so qubit is passing through a public channel and you try to observe them, you trying to measure them, then what will happen? It will be destroyed. It will either collapses to 0 or 1. So their super fragile quantum state collapses to either 1 or 0. This means a hacker cannot tamper with the qubits without leaving behind a telltale sign of the activity. So from this, you can say that, okay, quantum communication means secure communication. Another thing is no cloning. Classical domain cloning is possible, but you know that in quantum domain, we cannot have universal cloning machine. If you know the basis, you can construct cloning machine in that basis. For 0, 1 basis, you can construct your cloning machine is C0. But for plus minus basis, Hadamard basis, you also can design a cloning machine. But the same cloning machine won't clone 0, 1 state, or your C0 won't clone plus minus state. So universal cloning machine is not possible. So this is the results. This is the proof. I am skipping that also. It is available in Lin Sun Chuang also. You can go through that for students. Another thing is that indistinguishability of non-orthogonal states. If you are given two states, suppose 0 and 1 by root 2 0 plus 1, these are non-orthogonal to each other. You know that. So if I tell me what is 0 and what is 1 by root 2 0 plus 1. You cannot tell that with certainty or meaning with probability 1. There is a best strategy. Using that, you can distinguish 0 and 1 with some probability. That is 0.85 probability. You can tell this is 0, this is 1 by root 2 0 plus 1, but not more than that, not more than 0.85. You cannot distinguish this 0 and 1 by root 2 0 plus 1 with probability 1. So these three things: one, superposition; second, no cloning theorem; and third, indistinguishability of non-orthogonal states give you the security in quantum domain. In classical domain, we have to depend on some mathematically hard problem. You know, factorization, discrete log problem. So all those kind of things. In quantum domain, we don't need that. That quantum mechanics gives us this security. So speed, another thing, we can instantly transmit qubits from one part to another part, speed of light. Entanglement makes it possible to communicate instantly across arbitrarily large distance in principle. Not that simple, we need quantum repeater. So that is another story. I am not covering that in this talk. Possible to transmit highly sensitive data based on process called quantum redistribution or QKD. You know that. In theory, at least, these networks are ultra secure because of this no cloning, indistinguishable non-orthogonal states. Needs more careful study for actual implementation. Now here, this. So what is, in brief, what is that key distribution thing? So the main idea is to establish a symmetric key between two parties. One is Alice, transmitter, another is Bob, receiver. So you want to establish a secure key between these two parties. So how we will do that? We will take a bit string of 0 and 1, classical 0 and 1. We will encode this 0 by quantum bit, either this 0 or 1 by root 2 0 plus 1, two non-orthogonal states, and 1 by either this 1 or 1 by root 2 0 minus 1, two non-orthogonal states. And then we will send these qubits to the receivers. What receiver will do? Receiver will measure these qubits, either this 0, 1 basis or this 1 by root 2 0 plus 1, 1 by root 2 0 minus 1 basis. After all this qubit exchange, they will discuss their bases and they will keep the measurement results where their bases match. And they will discard the qubits where their bases mismatch. After that, they will do classical post-processing. It consists of error correction and hash function. That is completely classical. There is no quantum. So quantum part ends after qubit exchange. So this is the idea. And the security comes again from no cloning. Here we are sending two non-orthogonal states. So because of that, there won't be possible to mount any universal cloning machine, or it is not possible for Eve, the adversary, to distinguish two non-orthogonal states, as we discussed earlier. So that is why we have to send the non-orthogonal states. So this is the table, how Alice is preparing his heart states, how Bob measuring his states, and from where the qubits. So look, here bases match. So raw key are generated from this instance. So the protocol is provably secure, but again, theoretically, it is written in red. Based on no cloning theorem, we already discussed that. The proof comes from the quantum property that information gain is only possible at the expense of disturbing the signal. You already know, if I want to extract some information, I will I some telltale sign of my information extraction. If the two states we are trying to distinguish are not orthogonal, it is not possible to distinguish them. The protocol is a method of securely communicating a private key from Alice to Bob. Now the thing is, this is the partial list of available commercial QKD boxes in international market. In India also, there are many companies, they are selling this QKD box. Now the main thing, if we blindly depends on quantum mechanics. So theoretically, any QKD system provides unconditional security. This is correct. From quantum mechanics, we are that. Even if the adversary has unbounded power of computation, still he or she cannot extract the final key. However, inherent imperfection of the devices or deviation from the security models can result potential security breach in practice. Example, laser damping attack, PNS attack. If your source is not single photon source, if it is multi-photon source, then what will happen? This PNS attack, we can mount PNS attack. And we through this PNS attack, we can extract all the information about the raw key. Like conventional cryptographic modules or network devices, QKD modules are expected to have strict security testing. But unfortunately, we don't have that. We are just blindly use that. But blindly using that will create, we may put us complete destruction. So that is my message in this talk. Intensive and strict evaluation is an essential step before QKD is widely accepted by our government. In this direction, ISO, what is ISO? International Organization for Standardization and Electrotechnical Committee, specifications for QKD modules. It is expected that the manufacturer should follow QKD, and evaluators should also follow the procedure to test and evaluate the security of QKD modules, reducing the risk of being vulnerable. So without this, quantum mechanics is giving you the protection. Now we can divide QKD into two parts. One is DVQ, discrete variable QKD, another is CVQKD, continuous variable QKD. BB84, Eckart, those are DVQKD. Cow protocol, there is one protocol, that is cow protocol. It is called cow protocol, coherent one-way protocol. Orijit is working on that. So he is Orijit. He is working on that. That is CV protocol. So we can divide that again. We can divide QKD protocols by architecture into three categories. One is PM QKD, another is MDI QKD, another is EM QKD. What is PM QKD? That is preparation and measure QKD. Transmitter Alice will prepare states and receiver Bob will measure the states. MDI QKD, there will be another party called Charlie. So Alice and Bob, transmitter and receiver, will send states to that Charlie. He or she will do some Bell measurements, and based on her measurement result, Alice and Bob establish the keys. That is MDI QKD. EM QKD, entanglement based QKD. BB84 is PM QKD. MDI QKD is called MDI QKD, proposed by Low, Kurti and Kai. EM QKD, this is entanglement based QKD. What is entanglement based QKD? They are again a third party. He or she will give some entanglement, distribute entanglements between Alice and Bob. Alice will measure hard states in some bases, Bob will measure his states in some basis, and then they will discuss, and through their discuss, they will keep like PM, they will keep where the bases match, they will discuss where the bases mismatch, and from that the Rocky will be established. Now, this is the entire picture. Now, in QKD, what we are using? Optical source, detector for measurement, optical source for preparing states, detector for measurement. Then some post-processing. We said that after Rocky establishment, we need error correction and privacy amplification. So that is classical part. So post-processing part. So vulnerability, we can use all these modules to mount some attacks. So we can use optical source flaws to mount PNS attack, phase remapping attack, wavelength dependent attack, and through that, those attacks are very important because through that we can extract all the information about Rocky. Optical detection vulnerabilities, efficiency mismatch of single photon detectors at Bob's end. If there are efficiency mismatch between the detectors, then using that, adversary can extract the information, can distinguish zero when zero is coming or when zero is measured and when one is measured. Parameter adjustment vulnerabilities, time mismatch vulnerability between transmitter module and receiver module. So before QKD, receiver module Alice and transmitter module Bob, they need to establish some parameters. So if there is some time mismatch, using that, adversary can mount some attack. Classical post-processing, in classical post-processing, we are using hash function, we are using error correction code. If those, we will extract information regarding the secret key. So these are the list of the attacks which can be mounted when QKD is in implementation. Now, what to evaluate? So how we will evaluate this QKD? So first we have to test quantum state transmission, that is the source. Then other post-processing primitives, test parameter adjustment procedures. So everything we have to test. Then we can say, okay, this QKD box is safe for use. And how we can do that? If the module for that, we need some emulator. What is emulator? Emulator is known answered thing. So we know we will give some input. There won't be any security. So the emulator, we know the code, we will give some input, we will get some output. So if this QKD box follows my code, then what will happen? The same, for the same input, that QKD box will output the same thing. So through the matching, we can certify that the QKD is okay or not. So that is the, so we need emulator. If module under test is a QKD transmitter, so Alice's part, then we need some receiver module emulator. And if the QKD test is receiver, that is Bob's part, then we need transmitter emulator. So what is emulator? This is the emulator. Here we are testing TX module, that is transmitter module, part of Alice. That is why we need RX emulator. And here we are testing Bob's part, RX module under test. So we need TX emulator. So if this part follows the will be same for both the cases. From this output, we can certify where this is okay or not. Without this testing, it might be very risky to deploy these QKD boxes. So in a nutshell, many companies, research laboratories are claiming QKD hardware. However, without proper evaluation, it is very risky to deploy those devices in the network. It may cause potential information leakage if not evaluated properly, even if the QKD protocol has robust security proof. Security proof assumes that we are using single photon source. Security proof never consider the things we are discussing now, the loopholes in practical implementation. We need to keep in mind that there is a non-negligible gap between the theory and practical implementation. When QKD demands the detection of the footprint of eavesdropper if he or she tries to extract the information, there are several examples where eavesdropper can steal significant amount of information without being detected. So we should keep in mind Feynman first principle. You must not fool yourself, and you are the easiest person to fool. Let people to fool you, but you don't fool yourself. Don't keep in mind that QKD, it is coming from quantum mechanics, security is coming from that. So if someone gives me QKD box, it is giving me a complete security. No, that is not the case. Now the device independent security, another security checking. This is the black box kind of thing. What is black box kind of thing? You cannot see any circuit inside QKD. You can only give some inputs and will get some outputs. So studying that input output statistics, you have to certify the QKD boxes. That is called black box testing, and this is also called device independent security. We don't need to rely on the devices. Let the devices flawful. So this is the device independent kind of thing. I am not going into the detail. How much time is there? 5 minutes. Yes. So I am not going into the detail. So for this device independence thing, we exploit two kind of thing. One is Bell inequalities or CHHS inequalities. Here I am showing you the gaming version of this CHHS inequalities that is exploited to certify whether the QKD box is okay or not. So what is that game? So there are two versions of the solution. So let me state the games first. So there are two players, Alice and Bob, and one referee. Referee will give some input bits to Alice, say X, and some input bits to Bob, say Y. After getting the input bits, Alice will output the bit A and Bob will output the bit B. They will win the game if this A or B equal to X and Y. And the condition of the game is that after getting the inputs, when game starts, before game, you can communicate among yourselves and settle on a strategy. Whatever you wish, you can do that. But when game starts, you cannot communicate between yourselves. And you should be far apart from each other. And in this case, it can be shown that if Alice and Bob outputs the same bits, irrespective of their input bits, say 0, 0. If they output 0, 0 all the time, they will win the game 3 times and will fail 1 time. Similar for 1, 1. So their winning probability is 3 by 4, that is 75%. But if we use some entanglement and some strategy, I am not going into the detail, it can be shown that we can enhance this probability up to 0.853. So this can be utilized as the distinguisher to distinguish between quantum paradigm and classical paradigm. So CHHS inequality, violation of CHHS inequality, violation of BL inequality, that can be used as a distinguisher. So today afternoon, actually myself and Gautam, we are discussing about that. And another distinguisher, so using this distinguisher, Umesh Fajirani and Thomas Vidic, they proposed fully device independent quantum redistribution protocol 2014. And another distinguisher, that is actually pseudo telepathy. You may know about pseudo telepathy. This is n partigram. So n must be greater than or equal to 3. So there will be n number of players. Between the players who will share n JJ states, that is 1 by root 2 n number of zeros plus n number of ones. And then what here also one referee will be there. Referee will distribute some input strings. The constant is that input strings must be even, input string contains even number of ones, or the weight of the input strings must be even. So and after getting that input bits, what players will do? Players will apply Hadamard gate on his or her respective qubits, and if the input bits are 1, then players will apply S gate. What is S gate? S gate converts 0 to 0, but 1 to I1. So if the players are doing that, then what will happen? It can be shown that this is the winning probability of the game. Sum over yi, this is the output of the players, and xi, this is the inputs of the players. So sum over yi, varies from 1 to n, will be equal to half of sum over xi, I varies from 1 to n mod 2. If these are equal, then the player will win the game, otherwise they will fail. And it can be shown, I am not going into the detail, this in this slides you will find the strategy and all the calculation. It can be shown in classical domain, the best strategy will give you this probability, success probability, half plus 2 to the power minus n by 2. So if n increases, your probability will increase. And in quantum domain, what will happen if you use GHZ states and follow the strategy that if it is 0, then apply Hadamard gate. If it is 1, apply Hadamard gate and S gate. Then it can be shown the probability of success will be 1. So each and every case, you will win the game. So what is the difference between classical domain and so this must be minus. So this is 1 minus half minus 2 to the power minus n by 2. So you will get better difference in this case. So this is the stronger distinguisher than CHHS distinguisher. But the only thing is that CHHS played between 2 players. For this, you need at least 3 players. So this is the calculations. I am not going into this. In this, in 2019, we proposed some device-independent quantum free distribution protocol, which is accepted in the IndoCrit. In this protocol, sure telepathy game is exploited to certain dependence. So, but there are some challenges. But this technique, this black box testing, is not available till date. Why this is? Because of these challenges. So, locality loophole, memory loophole, freedom of choice. What is locality loophole? The entanglement cannot be generated locally. That is, there must be sufficient distance between the boxes. So it cannot be done in laboratory setup. Memory loophole, all the rounds must be IID. This should be not, there shouldn't be any memory which can store the information of the earlier events. So you must be sure about that. If there is something, some memory is there in your devices that preserves the information of the earlier events, then classically we can mimic this game. Classically we can get probability 1. Freedom of choice, the dimension of the subsystem must be 2-dimensional, that is qubit. Loophole free Bell test or CHHS state is still a challenge. Though in some recent paper, this is the paper, the loophole field Bell state has been reported. The commercial product for DIQKD is still not reported for this reason. So, in summary, so now we should conclude the so quantum computer are real threat to RSA-ECC, you know, because of Shor algorithm. Post-quantum cryptography, this is another avenue parallel to quantum cryptography, QKD, all those kind of things, that is quantum cryptography. There is another parallel avenue that is called post-quantum cryptography, and it is completely classical. There is no quantum kind of thing here. So that is code-based and lattice-based, believed to be hard in quantum domain. alternative solution, quantum cryptography, quantum cryptography has been proven secure. QKD, QRNG devices are already available in international market. But to the best of my knowledge, no DI-QKD or DI-QRNG devices are available in the commercial domain because of the difficulty in loophole-free build states. Okay, so thank you for listening me.
Thanks. Any questions?
This comment, discuss the pseudo-telepathy game, no? So Richard Cleve and Mitchell, they have a work on for the binary constant system, and using the Speres-Marmin square, they have actually shown how to construct a two-particle pseudo-telepathy.
Okay.
It is possible.
Okay.
Speres-Marmin square or pentagon, it has to be. Maybe it is not first their work, first probably Arvind he has done, but in their paper it is very
okay. Okay. Thank you.
Yeah.
You showed that in device independent QKD that locality loophole, but I have seen in one of the papers where they it was by Umesh Vazirani in one of his paper where they use computational belt test. So like the post quantum cryptographic functions, they use those functions to verify a quantum computer, its quantumness.
So post quantum is not quantum, first of all.
Yeah.
Post quantum is completely classical kind of thing.
Yeah, but they are doing this those belt tests on a quantum computer to verify its quantum advantage. So
Quantum, so they are doing CHHS test because
based on those post quantum cryptographic.
So post quantum is not quantum, first of all. So how can they implement post quantum into quantum computer?
They are like sending some functions to the quantum computer, post quantum, and then those quantum computer will solve those computations and will generate a state. Let's say, and will generate a state, a superposition state. This function will not be inversed actually. These are hard, classically hard to use.
So without reading that paper, I cannot comment. So what are you telling?
Let's thank the speaker once again. So, now we are going for a tea break. I think we should have tea break combined with the poster session because we have lost some time during this session. So we will be back here at 6 sharp because our speaker will be waiting online. So we have to be here at 6.